Swayam Prabha. Digital India. Educated India.
Welcome back to one more lecture on Introduction to Soft Matter. Last time we were discussing the solution to the general case, the case of the nth n models together, and what we saw was that there is the constitutive relationship basically becomes a sort of a generalization of the previous case where we had polynomials on both sides in powers of d, and now you have basically the same thing where the power on that power on each side is determined by the number of elements that we have. Okay. So, we had come to the conclusion that when we take the Laplace of the polynomials, we end up with a simple expression like this if we write it in terms of the polynomials. So, now let us go ahead and look at the different cases. So, first thing we will do is look at the stress relaxation function. Look at the stress relaxation function, where you are basically going to impose a strain, a step strain, which is again epsilon naught into h of t. So, the Laplace of this is already known and it is very simple, it is epsilon naught by s. Right. So, then the stress relaxation, so in this case, so then once you apply this to the previous expression, what you get is, so applying this to that previous case, you end up, so this implies that your Laplacian of the stress function looks something like this. You will have epsilon naught by into s multiplied by this q naught, you have n terms here q n s to the power n, and then on this side you have all the different, all the n terms multiplied together, right. So, this is, sometimes I will leave this in the factored form when it is easier for us to discuss. So, here I am just leaving it in the factored form. So, now what we are having is basically this is in a rational fraction form, right. And the question is, we cannot take the Laplace inverse of this, we have to express it in some simpler format. So, you can show that for this rational fraction, this is equivalent to some constants, and now the fractions can be, you can just take the individual terms here and you can go on constructing your all the terms till g n, and for the g n case you have a denominator that is s by E n plus 1 by eta to the power n. So, we have n plus 1 constants. So, where these are all new constants that we are introduced. So, g naught till all the way till g n are constants that have to be determined. So, how can you determine g naught till g n? Well, you can equate the two sides. So, the two sides what we are claiming is that these are the same. And this is the same as your epsilon naught So, you can take this entire denominator here, bring it over here, multiply this, and you will end up having both sides will be two polynomials, and here also you will have powers of s going from the 0 to n, and you on this side you again have a polynomial, right. So, you will equate all the different coefficients for the different powers, and from that you will be able to end up getting, you will be able to determine all these different constants. So, the different powers will give you n plus 1 different independent equations, and you have n plus 1 unknown. So, you can solve for them. So, in theory it is solvable, something it is going to be very cumbersome in terms of algebra here, and we are not going to do that. So, what we are going to assume is that now that these constants can be uniquely determined, right. So, to determine g of t, which is what we are after, take the Laplace inverse. And when you do the Laplace inverse, you see that, which is the same as g t, becomes, so the first one is g naught by s. So, that is will simply be g naught, and in each of the other cases you will have some this g 1 multiplied by an exponential function, right, and the exponential function will be such that it will be t by eta 1 by e 1, right, and all the way till g n. So, there are, so this, so now here there are n characteristic time scales associated with g t, and the time scales are such that you have lambda 1 equal to eta 1 by E 1, and similarly you have lambda n eta n by E n. Okay. These time scales are also called the stress relaxation time scales, okay, or sometimes often called the relaxation time scales. So, what we have done now, we can again redo for the creep response. So, we said, so we did the stress relaxation function. So, now we will do the other one, which is the creep compliance function or the creep response issue that we have to look at. So, let us look at the creep response. So, in this case you will just have the opposite. So, you are looking for epsilon at the Laplace of the strain, and that is going to be some sigma naught by s, and the numerator and the denominator will be flipped this time. So, you have on the numerator s by E 1 plus 1 by eta 1 and all the way till all your n multipliers, and on this side you have this q 0 plus all the way till q n s n. So, this entire thing again can be factored just like we had done it for the previous case. This is again a rational fraction, and the same this Rastein fraction can again be written as sum j naught by s plus j 1 by s plus some lambda, and I am going to call this creep 1, and the same way till j n s plus lambda. I said that this denominator is not easily factorable, but this is still a polynomial. So, you will have your different roots will be there. So, if you determine all that, then you now have to determine j naughts and all these different constants, right, and they are all, because this previous equation is given to you, these are all again determinable. Okay. So, where j naught, j 1, j n and lambda c 1 are model dependent constants, right. So, you have to now take the Laplace inverse of this to get the creep response. So, your epsilon t by sigma naught, which is the same as the creep compliance function, is now going to be some j naught plus j 1 e to the power minus t by lambda c 1 plus and all the way up to j n e to the power minus t lambda c n. Okay. So, note that there are again n characteristic time scales in the system. There are n characteristic time scales in the system, and these time scales are not different from the ones that we had for the creep for the stress relaxation function. Okay. So, these characteristic time scales there are also n, but they are different. So, these time scales are also called the creep or relaxation or retardation time scales. So, the appropriate time scales actually depends on the particular function that you are looking at, and if you are looking at the stress relaxation function, then you will have in a model with n parameters, you will have n characteristic time scales which are called the relaxation time scales, but if you are looking at the creep function, then you will also again have n time scales, but in this particular case they are called retardation time scales. Okay. So, now that we have been able to do these particular two cases, let us turn our attention to the case of the response to the arbitrary stress, to an arbitrary stress or strain history. So, we saw that you can define a Laplacian which is 1 by s times of q bar of s, and when we take the Laplace inverse of this, we end up getting the stress relaxation function, right. And we also know that this relationship holds, this particular relationship is also true, right. So, if you combine these two equations, so the equation this one which relates the ratio of the stress, the Laplacian of the stress and the strain to the different polynomials, then you can write then in previous case you can write that sigma bar s is equal to s times g bar of s epsilon bar s. And just like what we had done previously, we want to take the Laplace inverse of this entire quantity on the left. So, what you are going to do is you are going to club, you are going to take this separate and you are going to club s and epsilon bar s, and here you will add this initial condition, subtract the initial condition and add it. So, you end up having you will end up having these two expressions. And then when you take the Laplace inverse, so take Laplace inverse, and then you will end up with sigma t is equal to and then here you have okay. And remember, this is now we are going to introduce a demi variable. So, I can just introduce s or I can introduce any other quantity, but this s is going to be different from the Laplacian. Okay. So, just please keep that in mind. I am keeping s because I just want to be consistent with what we have done till now, right. So, just a note, this s does not relate to Laplace transforms. Okay. Okay. So, voila, what we have is this expression which we have seen before. We have derived this for the general case, but we had seen this expression before also when we had derived it for very special cases. So, if we go back up, we will see that we have I am just trying to quickly find that expression. Okay. So, we had derived this particular expression for a special case, and this special case was for this particular equation, right. So, for this simple case of the model, we had seen that when you take the relationship between an arbitrary given strain history and stress, the current state of stress is given by this particular integral, right. And it so happens that when you rederive it for the case of a more complicated system with n number of elements, you end up getting back the same equation. So, this shows that this particular equation is more fundamental in nature, and it is not really related to the models and the particular model that you have chosen. And you can show this, that this is generally applicable to the case of linear viscoelasticity, right. So, just like what you have for the stress given an arbitrary strain history, you can rederive the case of the strain for an arbitrary stress history, right, when we flip the two. And what you will find is that the expression just looks very similar to this one, and that expression will now have j instead of the g that we have here. So, that expression, that exercise is left, the derivation of that is left as an exercise for you. So, you can rederive. So, similarly you can show that your epsilon t is equal to sigma 0 plus. So, instead of g you will have the j, the creep compliance, and here you will have a very similar convolution integral, and instead of j you will have j, instead of g you will have j. Okay. It is becoming a bit of a tongue twister here. Okay. Right. So, these two expressions are going to be very important to us, and they will be used quite a bit. And a simple note that in some of the books you will not find, you will find this expression in a slightly different format. Okay. And here if you look at this integral on the left hand side, right hand side, you see that it goes from 0 to t. Okay. It is a definite integral, and the lower value of time here that we have input is 0, but you can also put minus infinity to the current time t, in which case this particular expression will simply be merged with the integral, and you will just be left with the one convolution integral. Okay. So, often in some of the books you will find this expression in a slightly different format, and just because it exists in a different format does not mean that the two equations are any different. In this particular case, you just have to recall that we have always assumed that there is a jump at t equal to 0. So, this particular expression is valid for that kind of a case. So, the last maybe I just want to do another sample problem where, okay, so sample problem. And we have seen that this formulation of the stress and the strain in terms of two polynomials seems like a very generic idea that would be valid for different kind of models that you would want to apply. So, it is only that the constants and the slight form will change given from one model to another, right. So, let us ask ourselves that if you have n Kelvin-Boyd models, and this goes all the way till n. So, this is eta 1, E 1, so this is E n, this is eta n, and let us say there is a last spring there. So, you have n Kelvin-Boyd models and you have one spring. Okay. So, can we rederive the force deformation relationship and see whether or not it falls in the same category as what we had done for the N-Maxwell, right. So, the only thing what I am trying to do is we had shown that this particular form, this form we had gotten from the Maxwell models in parallel, right. So, what happens if we put a lot of Kelvin-Boyd models, Kelvin-Boyd Mayer bodies and one spring in series like this. Okay. So, what are, so there will be, so each of these different bodies will have, when you apply a certain amount of force, it will share a fractional part of the force. So, let us just say that each of them is experiencing force F 1, another one is experiencing F 2 and all the way till F n. And this is this is another force here. So, from force balance, we can say that the net force has to be the same in all the cases, right, because these are all massless. So, these individual forces are no longer not a fractional part, it is actually the full of that. So, this is just F naught sorry, these are all equal and all the way and what is now going to be the geometric constraint on this system? The geometric constraint will be such that all of these will be experiencing different deformations. And then the total deformation delta x is now going to be a sum of all the different deformations in all the different units. So, now the next, so to solve it further, what we have to do is we have determined the force balance and the geometric constraint, that is they are quite straightforward, and then we have to write the individual force deformation relationships and then try to see how we can combine them into one equation, right. So, I will leave this here and I would like you to try and finish this problem as part of your self work, and we will begin with this particular problem in the next class. So, we will stop here today.